As promised in the previous video, we're going to look at the densest possible way we can save information. Saving information actually at the bit level. And this whole series of 3 videos was actually inspired by a message I got from a student who was asking how you could save the state of multiple buttons on a page and then bring that state back. And I said the most efficient way to do that would be a bit string, which saves information on a bit level. In other words, if you have a byte, you can save the state of 8 buttons because you have 8 bits in a byte. And in a way, this program totally represents that question, because we have the 8 bits in a byte represented as checkboxes. If we compile and run this program and say I select bytes 0, 2, and 4 and say create bitmasks, you see the bits 0, 2, and 4 represented in the binary. Then in the hex that would be a hex 15, and in decimal it would be a decimal 21. And if you want to understand what I'm talking about in more depth, you might look at a video 143 I did called Hex Dump, which goes into the nature of power series expansion number systems such as binary and our own decimal number system and hex. But if we look at the code for this, once again we're using an enum with a flags attribute, which allows us to have multiple values represented within the byte. And the bit values we use are 1, 2, 4, 8, 16, 32, 64, and 128, which represent the value of each of the bit positions within the byte. Once again, if you look at video 143, I explain that in detail. Then when we check the checkboxes and press the create bitmask button, the program basically goes through and checks if each checkbox is set. And if it is set, it takes the bit string that we've defined as a bitmask, and it does a or equal of bitmask dot bit 0, which is the symbolic values of 1, 2, 4, 8, and so on. I'm going to talk about bitwise operations such as OR, which is represented by the bar, and which is represented by a single ampersand rather than the double ampersand of the logical AND. I'll talk about these in detail in the next video, but essentially all you need to know in this video is OR with the bit string will cause that bit to turn on, so it'll become 1. And then we call the function display bitmask with the bit string that we've created with this series of ORs based on the checkboxes. And display bitmask essentially converts the numbers to the different radixes. Like it does a convert to string of the bit string that is, I need to convert bit string first to a byte because you can't pass convert to string a user defined enum. So we convert that to a byte, which is what it actually is, and then convert it to a string, and the default radix is 10, so that'll work for decimal without saying anything. But to convert it to hex, we need to have a comma and 16 for the hex radix, and that'll give us the hex number and the str hex. And then to convert it to binary, we need to use the 2 radix, which puts it in a string called str binary. And then in order to give a nice padded display so that it actually shows the whole byte, I use the string pad left method, which in the case of decimal I want to pad left 3, since you can go up to 255 to represent a byte, so we want 3 digits. And then 2, since you can go up to FF to represent a byte, and the hex digit. And then finally in the binary I have 8, because you can go up to 8 binary digits to represent a byte for the 8 bits that are in a byte. And once these are padded with zeros, I put them in the different text boxes we saw before. And in the form load, I use a bitmask in more of its conventional use, where I have 3 bits that I want to be turned on in the bitmask, and I have each of these ORed together in a statement, assignment statement, and then assign that to the bitmask and call our display bitmask. So when the form first comes up, I take the number that is created by these 3 bits being turned on, and I display that initially. And the reason I did that in the form load is I wanted to show more conventional use of a bitmask rather than representing checkboxes, which was sort of an answer to this student's question. I think his name was Malad. I'm probably totally mispronouncing it. Well, if we compile and run this program again, you could look at some interesting combinations, like I can turn on 0, 1, 2, and 3, and then do a create bitmask, and you'll see all the lower bits are 1, and all the higher bits are 0. And in hex this is 0F, and in decimal this is 15. And if we do the reverse, I turn on all the high bits and turn off all the low bits. You see you get all 1s in the high bits and 0s in the low bits in binary, F0 in hex, and 240 in decimal, which you see why hex is much better for representing binary numbers. You can see immediately what bits are turned on with a hex number, whereas with a decimal number you're going to have to work to figure it out. Well, I hope you enjoyed this video and learned a lot. And in the next video we're going to look at the bitwise operations for manipulating bitmasks and really why we use bitmasks. They're actually a holdover from assembler programming, which preceded using high-level language programming, and was concurrent with it for a while, but almost no one programs in assembler anymore. Assembler is getting down to the level that the computer actually works at, and nobody wants to do that. It's too much work. You need to write 100 statements instead of writing 3 or 4 statements in a high-level language. Well, I hope you enjoyed the video and learned a lot, and I'll see you in the next video on bitwise operation.